we are ready. Victor, please.
Yes, thank you. I give a talk on recognition of groups E63 and 2E63 by the Gruenberg-Kegel graphs. And this talk is based on a joint work with Khamova, Maslova, and Staroletov. All groups in this talk are considered to be finite. By P of G, we denote the set of all prime divisors of the order of a group G. And the prime graph, or the Gruenberg-Kegel graph of a group G, is built from abstract structural aspects of the group. The vertices are the primes dividing the order of the group, and two primes are joined by an edge if and only if their product is realized as the order of some group element. The prime graph was first investigated by Gruenberg and Kegel in the context of augmentation ideals of integral group rings in an unpublished manuscript that was later published by Williams. And as this talk, we will consider the next, let's say, property of a group G. We say that a finite group G is recognizable by Gruenberg-Kegel graph if for each finite group L, the equality of the Gruenberg-Kegel graphs implies that these groups are isomorphic. It is known that if a finite group is recognizable, then group is almost simple. And there are not really many examples of groups that are recognizable. So every new example of a recognizable group is important in some sense. In particular, if we talk about series E6Q and 2E6Q, recently Go, Kondratiev, and Maslova have proved that finite simple group E6-2 is recognizable, and a bit earlier Kondratiev proves that 2E6-2 is recognizable. And in this talk, we will try to understand why finite simple groups E6-3 and 2E6-3 are recognizable by the prime graphs. And we'll start with some notations and definitions. By S of G, we denote the number of connected components of prime graph of G. T of G is the independence number, that is the maximal number of pairwise non-adjacent vertices of our graph. TRG is the R independence number, that is the maximal number of pairwise non-adjacent vertices of gamma G, including a vertex R. And the structure of the prime graph has deep connections with the structure of the group itself. For example, an old result by Higman, that is, if we have at least three non-adjacent pairwise non-adjacent vertices in our graph, then group is non-solvable. The result of Gruenberg-Kegel that tells us that if the prime graph is disconnected, then there is at most one non-abelian composition factor of a group, and a more subtle result by Vasiliev that if two independence number of gamma G is at least 2, then there is at most one non-abelian composition factor of a group. And we provide the full version of results that I mentioned a few seconds before, because we will refer to it many times. If G is a finite group with the independence number is greater or equal to 3, and two independent number is greater or equal to, then, as I already mentioned, there is not at most one, but in this case, we have exactly one non-abelian composition factor that we denote by S in our group G. And the second and the third statement of this lemma are restrictions on the independence number and two independence number of Z non-abelian composition factor. In fact, T of S is greater or equal to T of G minus 1, and T2S is greater or equal to T2G in most of the cases. On this slide, you can see a picture of a Gruenberg-Kegel graph of E63. It is easy to calculate the independence number that is equal to 5 in that case, and two independence number that is equal to 3. So by conditions of lemma 1 hold, and we have S as the unique non-abelian composition factor of a group G with the solvable radical K. And on this slide, we will shortly discuss method we use to prove the theorem. Arrows on the slide related to steps of the proof. First of all, we show that this non-abelian composition factor is exactly the group E63. Then we show that there are no extra automorphism in group G. And the last step of the proof is to show that K is trivial. And actually, this method can be used in a general situation when we want to show that some group is recognizable by Gruenberg-Kegel graph. And now we will shortly discuss every step of this proof. And we will start with quasi-recognizability of E63. That is, we will show that this non-abelian composition factor is exactly E63. And in general situation, it is a success to show that some group is quasi-recognizable by Gruenberg-Kegel graph. But in this situation, this step is pretty easy because condition of lemma 1, by conditions of lemma 1, since 757 is not connected to a vertex 2, it means that this number divides the order of S. And since this prime divisor is pretty small, we, by the table of finite simple groups with prime divisors that are equal than 1000, we can list all the possibilities for S. And all of them can be easily rejected by considering P of S, the independence number, the two independence number, because the restrictions that lemma 1 gives us are pretty strong in this case. So the only possible case is S isomorphic to E63. Our next step is to show that there are no extra automorphisms in a group G. And for this, we consider gamma, that is a graph automorphism of order 2 of E6Q. And we have that the automorphism group of E63 is just the semidirect product of E63 by that automorphism. And it is known we know the structure of centralizer of this automorphism. It is F4Q. So in our case, it is F4-free. And if we suppose the opposite, that is J factored by K is not isomorphic to E63, then since Z of F4-free is divided by 73, there is an element of this order. So, and since this element is fixed by gamma, there must be an element of order 73 times 2. So these two vertices must be adjacent in our graph. But this is not the case because they are non-adjacent. So we arrive at a contradiction. The next step is a bit harder than the previous ones. We show that K is trivial. And for this, we need a technical lemma, lemma 2. If we have a normal elementary abelian subgroup N, and by H we denote the quotient group of G by N, and we define a natural automorphism of automorphism phi from H to the automorphism group of N, then prime graph of G is equal to prime graph of the semi-direct product of N by H with respect to this automorphism. In fact, it is easy to see that the solvable radical K is nilpotent. This is the direct consequence of Gruenberg-Kegel theorem. And by lemma 2, we can assume that K is an elementary abelian P group for some prime P in a connected component with a vertex 2. So we know the restrictions on the order of K. And now we will show that K is indeed trivial. First of all, we show that the prime divisors of K can be lie in the set 3 and 13. Suppose the opposite. If there is a prime that is not 3 and that is not 13, such that it divides the order of K by lemma 2, by lemma 3, we can assume that K is an elementary abelian P group. And since 3D4-3 is a subgroup of F4-3, and we know that J factored by K is isomorphic to E63, so we know that 3D4-3 lies as a subgroup in a quotient group. And the action of 3D4-3 on K is naturally defined by phi as in lemma 2. And since the order of 3D4-3 is divided by 73, there is an element of this order. And in fact, it fixes some point in some element in K. Therefore, there must be an element of order 73 times P. And since the only elements that are connected to 73 in our graph are 3 and 13, the statement of lemma follows. Now we show that K can be a free group. So 13 definitely doesn't divide the order of K. As in previous lemma, we suppose that K is an elementary abelian 13 group, and by second part of the proof, as I have mentioned, E63 is isomorphic to G factored by K, and it is known that CL5 subgroup of E63 are non-cyclic, and if we let L to be a CL5 subgroup of E63, and by L tilde, we denote the full preimage of L in a group G. We have that 5 element acts fixed point freely on L tilde. So the prime graph of L tilde consists of 2 vertices, 5 and 13, that are not connected by an edge. And it is a basic fact of on a Frobenius group that the quotient by a kernel is a cyclic subgroup. So, and since L tilde quotient by kernel, that is K, is a CL5 subgroup of E63, it must be cyclic, a contradiction with the fact that they are non-cyclic. And the last step of the proof, we show that 3 doesn't divide the order of K. We suppose that K is an elementary abelian free group, and F43, as we know, a subgroup of E63, and we let F43 act on K as an lemma 2. There is an element of order 73 in F43, and since this group is unisingular, there must be a fixed point of an element G. Therefore, vertices 73 and 3 are adjacent in prime graph, and that is a contradiction with the way our graph is constructed. So this step ends our proof, and actually the proof that 2x63 is recognizable by Gruenberg-Kegel graph is very similar to the proof we saw, because these groups are constructed highly similarly. That is all. Thank you for your attention.
Yes, Victor, thank you so much for your talk. Are there any questions or comments? Maybe. Okay.
I can give a comment if possible.
Yes.
Really, the question of recognition of a finite group by its Gruenberg-Kegel graph is rather hard for some reasons, and there are no many examples. Some survey you can find in our joint paper with Peter Cameron, which has been recently published in Journal of Algebra and available online. But these are just 2 examples. And the question how to find some infinite series is of interest. I think there are some more infinite series of groups which can be recognizable by their Gruenberg-Kegel graphs. But in any case, this is a very big area, which is only in some sense in start of research. So.
Yeah, thank you.
That's all.
Thank you, Natasha. And maybe which infinite family you plan to recognize?
For example, you can see a paper by Andrei Zavornitsyn. He has proved that regroups, it means 2 twisted groups G2Q, 2 G2Q are recognizable by their Gruenberg-Kegel graphs. And between E6 and twice E6, I think there are some groups which are recognizable by their Gruenberg-Kegel graphs, and possible between E8Q or E7, I'm not sure about E7Q, between EHQ and possible between some linear groups, since the Gruenberg-Kegel graphs have some special properties.
Yeah, I understand. Yeah. Thank you. Thank you for your comments. Are there any other questions or comments? If not, let us thank our speaker again.